All right, welcome to The Explainer. So glad you're joining us today. You know, if you're working with Oracle databases, you already know that performance tuning, well, it can honestly feel a bit like trying to solve a giant puzzle while totally blindfolded. But today, we're taking that blindfold right off. We're going to completely demystify SQL performance tuning in modern Oracle environments. And yeah, we're talking specifically about 19C, 21C, and the brand new 23AI. We'll dive into exactly how the database engine makes its decisions, why those decisions sometimes go just horribly wrong, and, most importantly, how you can see exactly what's actually happening under the hood.
Okay, let's dive into this. Here is our game plan for today, taking us from the problem all the way to the resolution. We'll hit 1. The lie of explain plan. 2. Capturing runtime physics. 3. Reading the matrix. 4. The nested loop of death. And finally, 5. Fixing the root cause.
So let's kick things off with a scenario that I absolutely guarantee has given you or maybe someone on your team a massive headache at some point. Picture this. You highlight a query in your IDE. Maybe it's SQL Developer or DataGrip. You hit run and it is lightning fast. Everything looks totally perfect. So you deploy it to production and then, bam, it crashes. Or worse, it grinds the entire system to an absolute halt. You end up wasting hours refactoring code based on diagnostics that looked perfectly fine. So what's going on here? Why do fast queries fail in production?
Well, the answer really boils down to a fundamental misunderstanding of the tools we use every day. Seriously, if you only take one single thing away from this explainer, let it be this golden rule. Never trust explainer plan. Think about the standard explainer plan tool like a GPS. It predicts this ideal, perfect route before you even pull out of your driveway, but it has absolutely no clue about the traffic jam, the sudden road closures, or the crazy weather you're going to face when you actually hit the highway. It's just showing you a prediction. It is not reality.
Which brings us right into Section 1, the lie of explain plan.
See, when you hit F10 to generate that explain plan, the database doesn't actually run your query. Nope. It just looks at the SQL text, glances at the dictionary statistics at that exact millisecond, and makes a completely blind guess. And it gets it wrong for 3 major reasons. First up, bind variable peaking. Explain plan doesn't actually know the real values of your bind variables. The optimizer might say pick an index if the bind value is active, but it would need a full table scan if the value was closed. It's basically just guessing. Second, environment differences. Your local IDE session settings like PGA memory limits or NLS parameters can be wildly different from the production application server, which means entirely different execution paths. And third, implicit data type conversions. The tool frequently misses these sneaky conversions that literally disable your indexes at runtime. Crazy, right?
All right, moving on to Section 2, capturing runtime physics.
So if we absolutely cannot trust the guess, what are we supposed to do? Well, we have to start measuring. To stop all this guessing, we use an absolute revelation in Oracle tuning. We inject a very specific hint directly into the SQL statement. I'm talking about the gather_plan statistics hint. This little snippet of text is just incredibly powerful. It basically forces the Oracle execution engine to attach a microscope to your query. As it runs, it records the exact number of rows processed, the exact memory buffers it touched, and the exact time spent on every single step of the plan. No more guessing.
Now, extracting this real microscopic plan is a super clean 3-step process. Step 1. Execute your query with that gather_plan statistics hint injected right in there. Step 2. Find the unique alphanumeric SQL ID that Oracle assigns to every single query. You can grab that from the View$SQL dynamic performance view. And Step 3. Extract the actual runtime data using the built-in package DBMS XPLAN.display_cursor. And hey, quick pro tip here, the absolutely critical parameter you need to include is all stats last. That tells Oracle to fetch the statistics from the very last time the query actually ran.
That leaves us nicely into Section 3, reading the DBMS XPLAN matrix.
Now, what's really interesting about this slide is that this is arguably the single most important screen a database admin or developer will ever look at, period. You're going to see 2 core metrics side by side. E-rows and A-rows. E-rows stands for estimated rows. This is exactly what the cost-based optimizer, the CBO, thought it would find based on its dictionary stats. E for estimated. A-rows stands for actual rows, the literal exact number of rows that step processed at runtime. A for actual. Comparing these 2 columns, that is exactly how we expose the lies.
But the real star of the show, the absolutely crucial metric, is right here. buffers, also known as logical reads. This number represents the amount of memory blocks requested from the database buffer cache. And listen to me carefully on this one. This is your ultimate tuning metric. It's the whole shebang. If you lower the buffers, you automatically lower CPU usage and disk I/O at the exact same time. Your entire goal when you're reading these plans is to hunt down the operations driving up those logical buffers and just eliminate them.
But here's the catch. You never read an execution plan from top to bottom. It's like a giant puzzle, because execution plans are actually hierarchical trees. You have to use the golden rule of traversal, which is the inside-out rule. You follow the tree all the way down until you hit the deepest indentation. That step executes first. And if two steps happen to share the exact same indentation level, the top one, the one with the lowest ID number, goes first. Basically, the data flows outward and upward from the deepest branches of the tree.
Okay, let's put this into practice in Section 4, the nested loop of death. Imagine this scenario. You've got a report that normally takes 2 seconds to run. Suddenly, out of nowhere, it's taking 45 minutes, and your CPU is absolutely pegged at 100%. Total panic mode, right? So, you inject the hint, you extract the runtime plan, and you compare those E rows to the A rows. And boom, you find a massive, jaw-dropping disparity, a difference of 850,000 rows.
Let's actually look at the matrix for this. Look closely at step 2, the table access full on the invoices table. The optimizer estimated it was going to find exactly 1 row. You can see the E rows is 1. So based on that completely bogus assumption, the database thought, hey, I only have 1 row. The fastest way to join 1 row to the next table is a simple nested loop using an index. But reality, the A rows showed the table actually contained 850,000 rows. And because the optimizer chose a nested loop based on that 1 row lie, it was forced to execute step 3, the index unique scan, a staggering 850,000 times. You can see it clear as day right there in the starts column.
The consequence of that cardinality misestimate is just brutal. Reading an index 850,000 times individually caused 4.8 million buffer reads. That, my friends, is the nested loop of death. That's exactly what's destroying your CPU and turning a quick 2-second query into a 45-minute total nightmare.
Which brings us to our final part, Section 5, Fixing the Root Cause. So we've successfully diagnosed the bottleneck. And honestly, this brilliantly illustrates the best part of all this. We can prove the developer's SQL code was never actually the problem in the first place. The code isn't broken, the database's perception of reality is broken. What happened was the statistics on the invoices table were completely stale. Maybe a massive overnight batch load had just finished, dumping hundreds of thousands of records in, and the automated stats gathering just hadn't run yet. The optimizer was simply lied to. And the resolution here is just so elegant, and it requires literally 0 code changes. All we do is manually update the table statistics using the DBMS stats.gatherTableStats package. By doing that, we are finally feeding the optimizer the actual truth about the table size. Instantly, the optimizer's E rows jump from 1 up to 850,000. And realizing that a nested loop would be fatal for that massive volume of data, the optimizer automatically pivots its execution plan to a highly efficient hash join. As you can see right here, by acting on runtime physics instead of blind guessing, and by fixing those statistics, we drop those logical buffer reads from a devastating 4.8 million down to just a few thousand. Our CPU finally breathes a massive sigh of relief, and the report execution time goes right back down to a snappy 2 seconds.
So, as we wrap up, remember that tuning Oracle databases in 19C, 21C, and 23AI means abandoning guesswork entirely. By leveraging gather plan statistics and hunting down those glaring disparities between estimates and actuals, you can ruthlessly eliminate the operations driving up your logical buffers. So I'll leave you with this question to think about the very next time you open your IDE. Are you optimizing your SQL for reality or just an Oracle hallucination? Thanks so much for joining me on this explainer, and I absolutely can't wait to see you dive into the physics of your own databases.